Hi, I'm Dylan Slocki, and we're going to be looking at supermassive black holes and galaxies and the similarities to calculations of gravitational Lagrange points. I hope you guys are all well. Diving into it. So the basic idea came about from what a limit of Lagrange point is. I was trying to figure out if mass can get trapped at a Lagrange point, could light get trapped at a Lagrange point, and how would you scale up this problem? You can't really do it on a planetary scale, so I would decide to scale it up on a galactic scale. What would that look like? And if light can get trapped on a Lagrange point, wouldn't that necessarily look like a black hole? So I'm going to be looking at that here. Going into the outline, we have physics, Lagrange points, black holes, calculations, results, and future research. Fundamental physics, I go from Newton to Kepler to Hilltop to saddle points. So most of you guys should know Newton. I don't know why you're here if you don't know Newton, but to recap, it's between two masses at a certain distance times the gravitational constant can show you the force of gravity between them. Kepler's laws. So you have two masses in orbit and one is going at a certain orbital velocity. Things that are closer in end up going faster to stay in a stable orbit. Things that are further out end up going slower to stay in a stable orbit. Hilltops, things that are on top of the hill, stay on top of the hill. Unless you push them, then they fall down. Saddle points, things that are in this axis fall back down like you're stuck in a valley, but things on this axis end up falling off like a hilltop point. So Lagrange points. The idea came about from the Italian-French mathematician and astronomer Joseph Lagrange. He was born in 1736, and I thought this was interesting. He was recommended by Euler to succeed him as a director of mathematics in the Prussian Academy of Sciences. So, thought that was great. You guys must know who Euler is if you're an engineer or far enough in physics or math. So, he attempted to solve the general three-body problem in 1772, which ended up resulting in Lagrange points. So Lagrange points have 5 points between two places orbiting, like a sun and Earth, or the moon and Earth, and basically they override Kepler's laws, where things that are closer in should be going faster, but because of the gravity of this point, it slows it down. Things over here should be going slower, but because of the combined gravity of these 2 points, it keeps it going faster. Now this is looking at the gravitational potential. You have L1, 2, and 3 unstable. They are the saddle points I showed you before. L4 and 5 are stable even though they are hilltops, which is kind of counterintuitive because you think if things fall off the hill, they're gone. But the Coriolis effect takes place and actually brings them back into a stable orbit. I'm not going to be diving into what a Coriolis effect has on this because it's not the focus of my research. I'm looking at the L1 point because I thought the gravitational effects there would be the most significant. So this is one of the most famous of the Lagrange points that we know of because we have Earth and Jupiter, the two more massive objects in our solar system, and you have the Greeks and the Trojan, the Hildas. And I actually have a video, but this slide does not want to play it, so please forgive me for being informal and leaving, but I wanted to show you this. This is a great diagram. You could see obviously 4 and 5 stay in the same area relative to Jupiter, but you could see that 1 and 3 end up just passing things in an orbit. So continuing on, I'm going to put it on this right here. Okay. So black holes. Black holes are locations in space that have extreme gravity. They're usually seen because of accretion disk, which is this beautiful thing right here, or stars orbiting close by. So they're extremely dense while relatively small. They're thought to be produced by supernova or when a large star collapses. There's a diagram that I could explain this, but hang on. This diagram is better at explaining it. So you go from nebula to massive stars to super red giants to supernova. The more larger of the supernova become black holes. The smaller ones become neutron stars. We don't really care about neutron stars, at least in this presentation. So, event horizon. It's a point around a black hole where the escape velocity becomes larger than the speed of light, so light cannot escape, hence it's a black hole. So remember this picture. This is the Milky Way galaxy. Supermassive black holes are thought to be in the center of most massive galaxies. They are between 1 million and 1 billion times more massive than a stellar mass black hole, and scientists are not sure why they are formed or how they are formed. This is another video by Keck and UCLA Galactic Center Group that does not want to play on this slide, so I'm going to show you right here. Thank you, Keck and UCLA Galactic Center Group. So you notice all these stars are orbiting this point, but there is nothing there. This is where a black hole is theorized to be. I'm going to theorize it's an L1 point between all these bodies. So this is actually an image of a black hole taken by the Event Horizon Telescope. This is the accretion disk. This is the black hole. Notice it's black. It is an international collaboration of a planet-scale array consisting of 8 ground-based radio telescopes. This is in the center of M87 galaxy. So there are 4 theories to the formation of a black hole. We have a number of smaller black holes coming in, combining together, collapse of a large gas cloud, collapse of a stellar cluster, and large clusters of dark matter. Dark matter are objects or areas in space that have gravitational pull, but there's nothing there. Kind of like a black hole, I guess, but people say that it's, I'll save it for later. My theory is that a Lagrange point between clusters of stars could be actually a black hole as well, having interesting gravitational effects, because if mass gets trapped at a Lagrange point, could light get trapped there? So going into calculations, remember this is a diagram from before. I did make my own for these calculations. You have M1 and 2 and the distance between an L1 point, and you have this equation. Now I am showing you this, which is this lovely picture right here. 100,000 light years across is 100,000 light years across. This is the Milky Way. I decided to split it in half. Assume it's a solid disk. Look at the center of mass for half a solid disk, and look at a star orbiting close by. And this is the M1 and M2. This is the L1 point, exactly where the black hole would be. I'm trying to figure out how far away the L1 point is from this calculation to where the black hole actually is, or the L1 point actually is. I do not consider relativistic effects, and I do not consider the mass opposite of this star, or actually in between the black hole and the star. So I decided to go with SO2 because it was the closest and has a short period, or one of the closest and has one of the shortest periods of 16 years, so there's a lot of data about that. Note the order of magnitude for some of these numbers, 10 to the 20th, 10 to the 42nd. These are huge numbers. This is in meters, but I do convert to light years later for all you guys who are astrophysicists. So notice this. The percent error is 10 to the negative 7th. This is the black hole distance to the Lagrange point. It's up to 9 kilometers away. This is the star distance to the black hole. So the orbit. Closest and furthest approach, and percent error. I thought it was very interesting, so I decided to look at other stars. You had a range between 16 light hours to 2,000 light hours approximately, looking at SO2, 8, 13, 22, and 66. This is a chart of all the data that I really love to see. Thank you, Gillison. If I pronounced that wrong, I'm sorry, but thank you to her and others, because this made it so much easier finding all the data in one place and not having any variations. So this is the calculation I did before. I put it in functions to make my life easier. And these are some of the functions. Note this equation right here is that equation right there. And in that equation, I am looking at the difference of what an L1 point is from where the black hole is. And you get the black hole location based on the closest and furthest approach of the data provided before in this page. So, I got a low battery, I have to wrap this up. So these are the orbits of all the stars, black hole in the middle, S22 is the furthest out. I thought this was very interesting. This is going from the star distance to the black hole and the L1 point to the black hole. This area fits my hypothesis, showing the black hole is right on top of the Lagrange point. The Lagrange point is right on top of the black hole. When you get closer in, it becomes off. I'm assuming that is from relativistic effects or not calculating the mass that is different from from other stars. Be interesting to see how this affects everything. Note, this is what I had before. When I note, it's 9 kilometers, 3.5 kilometers, 1 kilometer, 45 meters, 13 meters. This is for S66, between 7 and 13 meters, where its orbit is 10 to the 15, and the percent error is 10 to the negative 13. So that is 2 times 10 to the negative 8 light seconds, or 7 times 10 to the negative 16 for light years on the closest end. Very significant results. My conclusions go to say that the gravitational effects of a black hole might be caused from a multi-body Lagrange point. I believe if I was to do the calculation of the force at this point to figure out if the escape velocity at that point is the force is bigger than the speed of light, then this might give more evidence to being a Lagrange points being black holes. This might also explain in certain areas where you have clusters of stars, they might actually be have an effect on gravity around it and produce maybe more Lagrange black holes. I'm going to look into future research focusing on the intergalactic bulge to get rid of the outliers. Look at the area I was talking about, electromagnetic and dynamic effects, force on the L1 point, like I said, to see if the force is bigger than the speed of light, and relativistic effects, which I really do need to consider. Sorry for wrapping this up so soon, but my laptop is going to die. Thank you, IEC. I'm Dylan Slocki. If you have any questions about this, feel free to go back at the start of the video, look at my email, and email me, please. I would really appreciate any criticism, comments, or anything about this presentation. Thank you, IEC, and I hope you guys stay safe.